Hello and welcome to the third video of the FP2 chapter second order differential equations. Starter on the screen, write down the different particular integrals that you would try in each of these cases. Pause the video now if you would like to do this. Answers are coming up in 3, 2, 1, there they go. So in this video, we're not going to do too much new. What we're going to do is we're going to take what we did in the previous video, what we did in the previous chapter, using boundary conditions to find particular solutions, and we're going to apply that to non-homogeneous second-order differential equations using two sets of boundary conditions. So we're going to go through two full examples, and then in the next video we'll finish this off with some substitution. So with first-order differential equations, a constant of integration is needed. With second-order differential equations, two constants are needed, which means we need two sets of boundary conditions in order to find the particular solution. However, that might not be 4 separate pieces of information. What you might be given is 3 pieces of information and have the question worded in such a way that there are 2 pairs inherent in that. For example, if we jump down to part C here, you can see we're given the derivative is equal to 2 and y is equal to 1 at x equals 0. That is 2 pairs of information because it's saying that both of these are true when x equals 0. So the first pair is y equals 1 and x equals 0, and the second pair is dy by dx equals 2 when x equals 0. Quickly run through the question before we start. The first part, find the value of lambda for which lambda x cos 3x is a particular integral, so you don't need to try one here, they're telling you what it is and you just have to find lambda. Then we're going to find the general solution, and then we're going to find the particular solution given these boundary conditions here, and finally we're going to sketch the graph. I'm going to need space to do this, so I'm going to do one at a time on each screen. Here we go. Find the value of lambda for which this is a particular integral of this. So we're working on particular integral here, and they're telling us y is equal to lambda x cos 3x, which means the first derivative is equal to, don't forget your product rule, we're going to have lambda cos 3x when we differentiate the x part, and then we need to leave the x alone and differentiate the cosine, which gives us minus 3 sine 3x, and we still have the lambda x in there. The second derivative gives us minus 3 lambda sine 3x, and then again we need to do the product rule on this term. So if we differentiate the x part, we get minus 3 lambda sine 3x, and then if we differentiate the sine part, we get back to cosine, we get minus 9 lambda x cosine 3x. We can simplify that to minus 6 lambda sine 3x minus 9 lambda x cosine 3x. And then we put the second derivative, and in this case we don't need the first derivative except to find the second derivative. So we put the function in here and the second derivative in here, make it equal to this, find out what lambda has to be. I'll change into red to do that. So we've got minus 6 lambda sine 3x minus 9 lambda x cosine 3x, and that has to add with 9 lots of lambda x cosine 3x, and all of that has to equal minus 12 sine of 3x. That's good because we don't have a cosine on the right hand side for these cosine terms to equate with, so it's really good that they cancel, otherwise we would be stuck. Then we've got minus 6 lambda lots of sine 3x on the left and minus 12 lots on the right, so lambda equals 2, which means our particular integral y is equal to 2x cosine of 3x. We can use that to help us in part B, where we need to find the general solution of this differential equation. I've put the equation up here and the particular integral we're using here. Having found the particular integral, all we need to do now is find the complementary function, and that's using the coefficients of the left hand side. We've got m squared, there's no m, and then a 9. So we've got m squared plus 9 equals 0, which gives us m is equal to plus or minus 3i. And it probably shouldn't be a surprise that we get a complex number here, if we're using x cosine 3x as the particular integral, that probably means there's a cosine 3x as part of the complementary function, which is exactly what we find here. We have y is equal to e to the px, where p is the real part, so that's 0, which means e to the px is all 1, and then we have 1 times a cosine 3x plus b sine of 3x. So that's the complementary function. We already know the particular integral, so our final general solution, complementary function plus particular integral, is equal to a cosine 3x plus b sine of 3x plus 2x cosine 3x. And that is part B finished. Part C is the new part in this video, applying the boundary conditions given in the question to find the particular solution. So here's the general solution from the previous screen. Now we need the particular solution, and to do this we need to apply what we know. First of all, we know y equals 1 at x equals 0. Don't worry about the different notation here. They're saying g of x is equal to y. It's the same thing. Just make sure your final answer is a g of x equals rather than a y equals. So given that y equals 1 at x equals 0, we put those two in and see what we get. So y equals 1 when x equals 0, and that gives us 1 is equal to a times the cosine of 3x. Well, if x is 0, cosine of 3x is 1, so we just get a, plus b times the sine of 3x. If x is 0, that's a 0, so I get 0 b's. And then plus 2x cosine 3x, and because of the x as a multiplier in front, that is also a 0. So we get the very simple statement that a equals 1. Great, that gives us the first one. But now we need to find b, and we can't use this same information to find b. That's just going to tell us a over and over again. What we need is the second piece of information, that the first derivative is equal to 2 when x is equal to 0. If it was relevant, we could also use that y is equal to 1 in that, but when we differentiate this we won't have a y, we'll only have a dy by dx, so we won't need this information in this second one. So here what we're using is the fact that dy by dx is equal to 2 when x is equal to 0. Now to make this useful, I actually have to differentiate this. We don't know the derivative of this yet, so let me find that on the side in white. dy by dx is equal to a cosine 3x. If we differentiate that, we get minus 3a sine 3x, plus b sine 3x, we get 3b cosine of 3x. And then we need the product rule, plus 2x cosine 3x gives us plus 2 cosine 3x minus 6x sine of 3x. So this whole thing is equal to 2 when x is equal to 0, and when x is equal to 0, this term is 0, and this term is 0, which gives us 3b times 1, so we get 3b. So on the left we have dy by dx, which we're told is 2, and on the right so far we have 3b, and then 2 cosine 3x, so that's plus 2. And that tells us that b must equal 0. So if a is 1 and b is 0, then g of x must be cosine 3x. The sine term is not there because b is 0, and then plus 2x cosine 3x. And this is the final equation for the particular solution of this differential equation. The last part of the question asks us to graph this. Now graphing this is easier if you factorize. So let's have y is equal to cosine 3x, 1 plus 2x. I'm sure you recognize cosine 3x as a cosine curve that's just got a different period, so you've got more waves in the same period. When x is 0, this is just a 1, so you just get the cosine 3x, and when x is minus a half, you end up with a 0, so that all becomes 0. So those are two key points on your axes. But then as x increases, this bracket is acting as a multiplier, and your amplitude gets higher and higher as x gets bigger and bigger. So as you go along, you start off like this, but then it gets bigger and bigger and bigger. So if I were to sketch this, I would have those two key points at -1/2. This must be 0, and when x is 0, this is cosine 3 of x, which is a 1. So it looks something like this. And my diagram is probably not very good, so I have also put on an accurate plot to show you how it looks. There we go. Second and final example. Again, I'll just quickly run through the pieces and then we'll do them one by one. Find the general solution of this. Then we'll find the particular solution given our boundary conditions. And then we're told a little bit of context here. We're modeling the motion of a particle, and we need to find the minimum distance here and justify that it is a minimum. So hopefully the word minimum is already making you think, I'm going to have to differentiate this, set it equal to 0, justify the minimum. Hopefully that is making you think I need the second derivative and make sure that that is a positive value. But we'll come back to that in a minute. First, we need to find the general solution of this second order differential equation. So doing all of the things that we've done so far, we need the complementary function. Here we've got 2m squared plus 5m plus 2 is equal to 0. This will factorize 2m, m, that will have to be a 2 and a 1, which means m is equal to -1/2, or m is equal to -2. Now a quick note here on the variables. We're using x and t, and this is a little bit annoying, but quite common. In physics, if you do physics, you'll know that x is often used to represent displacement. But throwing it into a pure module, we're used to seeing x in this position and y in this position, so it's going to be very easy for you and me, as I go through this, to write y where I actually mean x in this question. So apologies in advance if I do that. So here we've got x for the complementary function is equal to ae to the alpha t. So that's ae alpha is -1/2, so minus t over 2 plus be to the -2t. Now we need the particular integral, and here I'm going to try a linear function because on the right hand side we have a linear expression. X is equal to lambda t plus mu. So the first derivative with respect to t is lambda, and the second derivative is 0. When we put that in, 2 times 0 is 0, plus 5 times lambda is 5 lambda, plus 2 times lambda t plus mu, 2 lambda t plus 2 mu, and all of that has to equal 2t plus 9. So equating my t coefficients, I get 2 lambda is equal to 2, which means lambda equals 1. And the constants, 5 lambda plus 2 mu, which we now know is 5 plus 2 mu, has to equal 9, which means 2 mu equals 4, and mu equals 2. Great. So our particular integral for x is equal to lambda t, so that's t, plus mu, that's 2. The general solution then, as usual, is the complementary function plus the particular integral. In this case, x is equal to ae to the minus t over 2 plus be to the minus 2t plus t plus 2. And that is the general solution in part A. Part B, we're applying our boundary conditions. Here's the general solution up here. And here are our boundary conditions. X equals 3 and dx by dt equals -1 when t equals 0. Again, we've got two pairs here. We've got x equals 3 when t equals 0, and the first derivative equals -1 when t equals 0. So we'll take these both one at a time. We've got x equals 3 when t equals 0. Let's see what that gives us. Put those into your equation, your solution. 3 is equal to ae to the minus t over 2. But if t is 0, e to the 0 is just a 1, so that's a. And same for the second term. If t is 0, e to the 0 is a 1, so that's a b, plus 2. And that tells us that a plus b must equal 1. Obviously, we will need the second one to create simultaneous equations in this case to solve for both a and b. So let's go for that. We've got dx by dt is equal to minus 1 when t equals 0. And again, I need the derivative of this equation. So I'll just do that quickly on the side here. Dx by dt is equal to minus a half a e to the minus t over 2 minus 2b e to the minus 2t, and then don't forget t, that differentiates to a plus 1, and the 2 differentiates to a 0. So if t equals 0, again, e to the 0 is a 1, e to the 0 is a 1 here, and the dx by dt we're told is minus 1, so this says minus 1 is equal to minus a half a minus 2b plus 1. Rearranging that and getting rid of the fraction tells us that a plus 4b must equal 4. From the first equation, we know that a is equal to 1 minus b. And that tells us that 3b equals 3, so b must equal 1, and if b equals 1, then again from the first equation, we see that a must equal 0, another 0. Which is quite nice if it's correct, because it makes this slightly easier for the third part of the question. So our particular solution, if we put those back in, x is equal to a is 0, so the first term is gone, b is a 1, so that's e to the minus 2t, and we've still got plus t plus 2. So this is the particular solution for these boundary conditions. The third and final part of this question is quite wordy. So it says the particular solution in part B, that's the one we just found, is used to model the motion of a particle p on the x-axis. At time t seconds, where t is always going to be positive, greater than or equal to 0, p is x meters from the origin O. Show that the minimum distance between O and p is this meters, and justify that the distance is a minimum. This is drawing on previous work. You know that a minimum distance or a maximum distance happens when the derivative is equal to 0. So we need to find the derivative of this first. So if we've got dx by dt, where x is the particular solution, not the general solution, that gives us minus 2 e to the minus 2t plus 1. The minimum happens when this is equal to 0. So that's e to the minus 2t is equal to a half if you rearrange. Logs of both sides, we get minus 2t is equal to log of a half, which I will note here you can then write as log of 2 to the minus 1, which is the same as minus log of 2. I think that will be useful later because we've got log 2 here, not log of a half. So when you then divide by the minus 2, that becomes half. In front, we get t is equal to a half log 2. At this point, pause and just remember what it is you're trying to do and what you found. This is the time at which the minimum distance happens. It is not the minimum distance, which is good because it doesn't look like this. To find the minimum distance, we need to put the time that happens back into the equation for the distance x. So when I put that back in, we get x is equal to e to the minus 2t, which we now know t is a half log 2, plus t, which is a half log 2, plus 2. Now this first term, the 2 and the half cancel out, and in order to simplify that with the e, I'm just going to use this backwards and see that minus log 2 is the same as log of a half. So e log half plus half log 2 plus 2, and now you can see that the exponential and the logarithm cancel out to give you a half plus a half log 2 plus 2, which is 5 over 2, plus a half log 2, factorize out the half, and we get the answer as required in the question. This is x, which is a distance, so the units are meters. The very last thing is to justify that this is a minimum. To do that, we just use the second derivative or any other method that you're happy using. I'm quite happy with this method. So we'll take the derivative that we found here and differentiate it again. And that gives us 4e to the minus 2t. And I hope you can see that any value that you put in here for t will give you a positive. Therefore, this is indeed a minimum and not a maximum. So there we've had 2 full examples, and I hope that is enough now for you to have a go at the questions in exercise 6c. And maybe I'll see you in the final video of this chapter for some substitution.